Good morning. Hopefully I'll be back soon, but until then I am going to go ahead and start the next section with you guys. You do need some paper out so you can take some notes. I do want you to take notes and upload the notes as an assignment, as well as there'll be an assignment at the end of this section that you need to complete. So there will be 2 assignments today. Again, the first one is making sure you get the notes, copying them down in your own handwriting, and submitting that online to Canvas. The second assignment is actually doing the assignment that I'm going to assign from the textbook, and then getting it turned in also via Canvas. So make sure you get those 2 things done today. So we're starting our next section. In our book, it's titled Integer, Exponents, and Scientific Notation. Well, for this section, we actually are not doing anything with scientific notation. So we're not covering that part of that in this class. Again, you guys have probably done scientific notation before, as well, though, as integer exponents. So some of this should seem like review to a lot of you guys. But this entire chapter, chapter 5, is kind of condensed a bunch of things into one. So starting off with some exponent rules. The first one is the product rule. Again, you guys should be somewhat familiar with this, but anytime we have the same base values, we can take numbers with the same base that are being multiplied together and add exponents. So again, this is our product rule. If we multiply 2 numbers with the same base, then we're going to add exponents. So in the example up here, they have a to the m power, a to the n power. The base stays a, and then you're just adding m and n. So actually looking at some number values here, we have 3 to the 4th power, 3 to the 7th power, and we are going to just multiply those by adding those exponents. So this would be 3 to the 4th power plus 7. So 3 to the 4th plus 7, well, 4 plus 7 is 11, so that's 3 to the 11th power. On the second one there, part B, we have 5 to the 3rd power and just 5. Well, even though there's no exponent on here, it's like it has an exponent of 1. So we're going to have 5 to the 3rd times 5 to the 1st. So that's the same thing as saying 5 to the 3rd plus 1, or 5 to the 4th. On C, right, now we have variables, but again, no different. We have the same base, so they all have a y in them. So again, we're just combining those values by adding all those exponents together. So 3 plus 8 plus 2. If we add all of that up, that's 13. So y to the 13th. And then finally, on this next one here, again, only looking at values that have the same base. That's what we're combining here. Well, we do have numbers out in front, so we can go ahead and multiply the numbers that are in front. So we have 5 times the negative 3. And then we're going to go ahead and group those 2 y's together. So I have y to the 2nd power and y to the 4th power. So again, just changing the way that's written, using our commutative property to move things around. Now we're going to add the 2 exponents together for the y values. So we have the 2 numbers out in front, multiply just like they normally would. 5 times negative 3 is negative 15. And we're adding these 2 exponents. Oops, sorry, that was still 4. It's going to be 6 once we add it. So negative 15 y to the 6th power. All right, so again, that's our product rule. The next rule is exactly this. Oh, actually, I'm thinking ahead. So 0 exponent is our next rule. We have if a is a non-zero real number, then anything raised to the 0 power is 1. So as long as a isn't 0, then our answer to this, raising it to the 0 power, will always be 1. So on the first one, 6 to the 0 power is 1. Negative 6 to the 0 power is 1. Now, this one we got to be careful because now we have a negative sign. Notice the negative sign here is not in parentheses, so it's not attached to what's being raised to the exponent. So the 6 is being raised to the exponent. So this would be the same thing as saying negative parentheses 6 to the 0 power. So just the 6 is being raised to the 0 power, so the negative is still there. So it's actually going to be a negative 1. On D, this too will actually give us the same outcome as the last one because now we have the negative in the parentheses, but the parentheses themselves will become 1, and then we still have the negative out in front, so we have -1. On E, both these values are being raised to the 0 power, so they're each going to be a 1. So 1 plus 1, which gives us 2. And the last one, the entire set of parentheses. Again, we don't even know what this variable is, but as long as it's not 0, then our answer to this will be 1. So that's the only exception there. So for that one, again, it will be 1, but there is the likelihood or the possibility that if k was 0, then it wouldn't work. So we do have to put one little stipulation here that the answer is 1 as long as k does not equal 0. Because if k equals 0, then it doesn't work. All right, for a negative exponent. So for a negative exponent, we have it's basically asking us to do a reciprocal. So we're going to take our a value, we're going to write the reciprocal, and then whatever exponent we have, the sign will become a positive, and it'll stay on that same variable. So very simple with these. We're taking this, we have a 2, we're going to rewrite the 2 as 1/2. The -3 goes on the bottom with the 2, but it's no longer a negative, it's now a positive. So this is just 1/2. Now, you could also simplify these further if you wanted to. So if you actually want to do the math there, 2 to the 3rd power is 8, so we could simplify it all the way out. All right. The directions in this part do say just rewrite it with a positive exponent, so it doesn't actually ask us to go this far. Just know that if we were to evaluate, you would actually want to simplify that. Same on all the other problems that we looked at so far. On part B, so we're going to take 6 to the -1. All we're doing is flipping it. So 1/6. So if to the -1, it's now a +1. We don't even have to write that. It's just 6/1. Sorry, 1/6, I mean. So that's our answer, 1/6. All right, on C, this entire thing is being raised to the -3 power. So that means that the whole thing is going to be flipped first off. So we have 1/5z to the +3. Now, this is working towards another property, so we could just leave it here because all he asked us to do is rewrite it. If we wanted to take this a step further, we could say that 1/5 to the 3rd, z to the 3rd would also work. On D, we have 5z to -3. Notice, this time there's no parentheses. It's the same exact thing that was over here on C, but there's no parentheses. So the only thing that the -3 is attached to is the z. So we still have the 5, and then the z is going to be flipped. So we have the reciprocal, and again, it's now a +3. And then whenever we rewrite this, 5, we multiply it to the top, so it just becomes 5/z to the 3rd. On the next one, notice again, we have our variable. The variable is the only thing being raised to the 2nd power here, not the negative sign. So we have 1/-m to the 2nd power. We could leave it like that. It really doesn't matter where you put the negative sign, whether it's there or out in front. Again, the negative sign was not attached to the exponent, so again, it doesn't matter where you put it. Same thing for F, but now we have parentheses and the negative is included. Why is that important on this one? Because now if we rewrite it, same way that we did the last one, -m squared will become a +m squared. So, because if we were to square something that's negative, the negative is going to end up canceling itself out. So again, it will just be m squared. On G, we have 3 to the negative 1 and 4 to the negative 1. So on each one of these, again, flipping these separately, we have 1 over 3. Again, we could put the 1 there. We don't have to because it's just the first power. So we have 1/3 plus 1/4. Now, if we wanted to keep going with this and actually solve it all the way, since it does say evaluate, we would need to combine those two fractions. In order to combine two fractions when you're adding, you'd want to change the denominators to like terms. So on this one, to get these both to be the same thing, they could both go into 12. So the first fraction multiplied by 4 on top and bottom, so we'd have 4 over 12. Second fraction multiplied by 3 on top and bottom, so you have 3 over 12. Add them together and you get 7 over 12. Same type of thing on number H, or letter H. Again, we'd flip these first, so 1/5 minus 1/2. If you want to rewrite that first, we'd have 1/5 and 2. Sorry, the 5 and the 2 would both go into 10. So rewrite this, multiply the entire first fraction by 2. So we have a 10 on the bottom. Multiply the top and bottom of the second one by 5. So we have a 10 on the bottom. Again, we need the same common denominator. So 2 times the top is going to be 2. 2 times the bottom will be 10. On the second part of this, 1 times 5 is 5. 2 times 5 is 10. Subtract them, we get -3 over 10. Now, these other two problems that are over here, we have a special rule. And before I actually get into the rule that's down there, I want to take a look at them first. So what this is saying is we are going to have 1. And then if we were to flip this and do reciprocal here, this would be 1 over 2 to the third. Well, this is like division, right? 1 divided by this. If we were to divide that, 1 divided by 1 over 2 to the third power. Anytime we divide, that's the same thing as multiplying by its reciprocal. So let's do another reciprocal here. 1 times, well, the reciprocal of this is just 2 to the third. So we end up with just 2 to the third. So the special property here is if you have a negative in the bottom of your fraction, then again, we're going to still do our reciprocal, and we can do the reciprocal of this whole thing here. Flip it, and the 3 comes to the top as a positive number. Now, it's only really moving whatever value had the negative exponent. So this 2 ends up coming to the top. On something like B, if we're applying this property down here on the bottom, so 2 has a negative value, 3 has a negative value, they're going to switch places. So we are going to have 3 on top to the positive 2, and 2 on the bottom with a positive 3. Now, one example I did not see in the book that I want to make sure that I mention is, let's say that we didn't have a negative on each of these. So I'm going to add an extra example here. We have, let's say we had 2 still, and we still had 3 down here to second power. And I want this to be negative second power. Let me make that a little bit clearer. So that's a -2. Well, what's going to happen here? The whole thing isn't actually flipping. There's no negative on the 2 on top. So the 2 essentially stays on top. The 3 will now also be on top. So if we wanted to evaluate this all the way, which this actually does say evaluate, so I forgot to evaluate on those first 2. I'll go back and do that. But now we have the 2 times 3 to the second power. Again, only the part that had the negative exponent moves. So this becomes 2 times, again, following your PEMDAS rules, your rules of operations. We're going to have, or order of operations, we're going to have 3 times 3, because we're doing 3 squared, that's 9. 2 times 9 is 18. And then over here, we have, just to continue evaluating these, 2 to the second power, that's 2 times 2 times 2. So 2 times 2 is 4, 4 times 2 is 8. On this one, 3 squared, again, that's 3 times 3, that's 9. 2 to the third power, again, that's 8, so that's 9 over 8. So those would be fully evaluated. Okay, so now this is quotient rule. Quotient rule is the exact opposite of the product rule. In the product rule, we were multiplying two values with the same bases, and we had to add their exponents. Now we're dividing two of the same base, and we have to subtract their exponents. So we have a to the n power over a to the n power, and we subtract them. Base stays the same. Again, this only works with same base numbers, but you subtract their exponents. So going over here to the first example, we have 3 to the 7, 3 to the second. That'd be the same thing as saying 3 to the 7 minus 2, which gives us 3 to the 5th. Again, all they're asking in the directions is to rewrite as a positive exponent, so we don't have to evaluate all the way. We can just leave it as 3 to the 5th for right now. We have p to the 6th and p to the 2nd. Again, subtracting those exponents. 6 minus 2, that's going to give us p to the 4th power. On this one, I have a couple ways that we could look at this problem. First, we're doing -2 minus 5. So just using this rule, I have 8, -2, minus 5. That becomes 8 to -7. Well, I want a positive exponent. I don't want a negative exponent. So I got to go back and use my other rule from the last slide to flip this. So I'd have 1 over 8 to the 7th power. Now, I'm going to redo this problem one more time up here. So we could choose to get rid of the negative part first. So I had this as the original problem. If I wanted to move this piece first using the old rule, I'd have 1 left on top. There'd be no other, this value would no longer be here. And I'd have 8 to the 5th times 8 to the 2nd, because I'm bringing this down to the bottom. I didn't have to move the 5 on the bottom because that part wasn't negative. So I'm just moving this one down. So now this would be our product rule instead of our quotient rule. And we'd have 5 plus 2, which is 7. So again, notice both of these come out to the same thing, whether I get the 1 over 8 to the 7th power or 1 over 8 to the 7th power. Again, same thing. So on F, we now have 6 over 6 minus 1. Well, this 6 on top, that's like it just has a 1 at the top. So this would give me 6 to the 1 minus a negative 1. Be careful of those signs because we're subtracting a negative. So really that's plus a positive. So this would be 6 to the 2nd power. On C, we have k to the 7th and k to the 12th. So k to the 7 minus 12, which is k to the -5. Or again, we got to flip this, so 1 over k to the +5. On D, again, subtraction. Now again, be careful with these signs, because when we subtract on this one, 7 minus -3, again, minus a negative becomes plus a positive. So we have 2 to the 10th power. On G, we have z to the -5 minus -8. Again, that's plus a positive. So that becomes z to the +3. Again, if you wanted to do this in a different route, similar to what I did on the one above it, E, you could have flipped these first. So you could have said, all right, we have z to the 8th over z to the 5th. Then subtract z to the 8 minus 3. Notice we still get z to the 3rd. With our exponent rules, you should be able to apply the rules in any order. It's not the same thing as doing order of operations. Again, these rules should be interchangeable no matter what order you do them in. All right, on H, we have a to the third, b to the fourth, as long as b is not 0. Now, I can't actually simplify that at all because these two don't have the same bases. Everything that we've talked about with these rules are when we had values with the same base. On number H, they don't have the same base. So since they don't have the same base, we can't do anything else with them. All right. Let's go to the next one. All right, power rule. So with power rule, if a and b are real numbers and m and n are integers, then when you have a number raised to a power and then it's raised to another power, the values that are in the exponents get multiplied. So a to the m to the n is the same as a to the m times n. And then here on part B in this example, this is what I was talking about earlier. I actually used this in one spot already. A times b to the m, it's almost as if it's getting distributed. It gets distributed to both parts. Well, it's like both of these have a 1 on them, so it's just being multiplied, just like it got multiplied here. So it would be 1 times m or just m on each of those. Same thing with a quotient. If we have any two values in a fraction like that, they're being divided, well then an m that's outside of parentheses, the whole thing is being raised to the m power. So that m goes to both the numerator and the denominator. So the a is to the m power and the b is to the m power. And then notice they keep making comments like this as long as b is not 0. Because remember, you can't have 0 in the denominator. So a lot of times there's some type of restriction when it comes to having variables in the denominator. So now, on here, this is just explaining what they did. Simplify each of the power rules. So again, just simplifying these as much as possible. We have 3 and 8. Again, we're just multiplying those together. So p to the 8 times 3 is equal to p to the 24th power. On B, again, this 4 goes to each of those. Again, it just says simplify. It doesn't say how it wants us to leave our answer. I'm going to go with simplest form. So let's actually multiply this out all the way. So we have 2 to the 4th power and 3 to the 4th power. And if we were to actually keep going with that, 2 to the 4th power, that's going to be 16 because 2 times 2 is 4, times 2 is 8, times 2 is 16. And then 3 to the 4th power, well, 3 times 3 is 9, times 3 again is 27, times 3 again is 81. For C, we have 3y to the 4th power. So again, that goes to both parts. So 3 to the 4th, y to the 4th. 3 to the 4th, we just said a second ago, was 81. So 81, y to the 4th. On D, we have a 2 on the outside. Again, it's being distributed to both of these. So again, this has a 1 on it, so it gets multiplied to the 7, multiplied to the 1. So this is 6 to the 2nd power, and p to the 14th power, because again, multiplying. Now, we can go ahead and simplify that a little bit more. 6 to the 2nd power is 36, p to the 14th. For E, we have negative 2, m to the 5th power, over z to the 3rd power. So that 3 goes on everything in here. So now notice, this was in parentheses. So it's as if this negative is also in parentheses with that 2. So it's going negative 2 to the 3rd power, m, to the 5 times 3 power, and then z to the 3rd power. Now, our exponent here is an odd exponent, so it's not going to actually affect that negative sign. So we don't have to do the parentheses. We could leave them alone. So if we wanted to, we could just leave this as negative 2 to the 3rd, m to the 15th on the bottom, z to the 3rd. We could simplify this. 2 -2 times -2 times -2 is going to give us a -8. So we could also rewrite this as a -8 m to the 15th over 2 to the 3rd. That'd be our answer. All right, this one is really just an extension of our negative exponent rule from earlier. If we have a negative exponent, it's going to give us the reciprocal and then a positive exponent. Well, same thing is true if we have an exponent that is negative on an entire fraction. It'll flip the entire thing and then give us the same fraction with the same reciprocal of that fraction with a positive exponent. So on the first one, 3 over 7 to -2, and we're flipping the whole thing, so it becomes 7 over 3 to the +2, which then you could distribute that 2 to both parts, so 7 squared, 3 squared, which becomes 49 over 9. Now, if you need proof that this works, and you could do your rules in a different order. So let's say we distribute the exponent first. We have 3 to the -2, and then we have 7 to the -2. So using our other rule that we had with our negatives, these are going to make these move. The numerator is going to go to the bottom. The denominator is going to go to the top. So we have 7 to the +2, 3 to the +2, which again comes out to the same thing, 49 over 9. So there's multiple ways that you could show that same work. On B, so same thing, and that's flipping the entire fraction. So we end up with 5 over 4 to the +3, or 5 to the +3 over 4 to the +3. 5 to the +3, 5 times 5 is 25, times 5 again is 125. 4 to the 3rd, 4 times 4 is 16, 16 times 4 is 64. And again, those are our answers. So these are all of the rules that we just did, all summed up together. So we have our product rule, our quotient rule, our zero exponent rule, our negative exponent rules, our power rules, and then those other special rules there are actually just more exponent rules. Now notice, every single one of these rules, when we have a variable on the bottom, says that the number can't be 0. That's because, again, if we had a 0 in the denominator, we get something that's undefined. So again, there are those restrictions anytime we deal with any fractions. Now, on here, this is just doing multiple rules at the same time. So a few more examples on A. So we have one that has a negative. We have the same bases. Again, you can go in a couple different orders here. Doesn't matter which one you do first. So for example, if you want to multiply these, then you can use your product rule and add those together. So you'd have 3 to the 2nd plus -5, which gives us 3 to the -3, which then we could flip that and be 1 over 3 to the +3, or 1 over 27. Again, is that the only way to do that problem? No. So let me tackle it a different way, just to show you that it does not matter what order you do these rules in. So we had a -5. Let's say we chose to flip that first. So we had 3 to the 2nd times 1 over 3 to the +5. So now just keep rewriting it. We have 3 to the 2nd on top, 3 to 5 on bottom. If we subtract that, we'd have 3 to the 2 minus 5, which gives us 3 to -3, which then gives us again the same 1 over 3 to the +3, or 1 over 27. Now, there's a couple different ways you can think about this fraction too. So let me go back one more time. From that fraction, another popular way to think about this is look for the difference between these. So the difference between those two is going to be 3. Where's the bigger value? It's on bottom. So I could also just say 3 to the 3rd power, nothing left on top. Because in that way, I'm canceling things out. Because remember, these are exponents. You could write it as 3 times 3 over 3 times 3 times 3 times 3. I need 5 on there. Oops, I said 5. I wrote 5. 5 3s there. So cancel them out, cancel them out, cancel them out. I got nothing left on top, so that's a 1. I got 3 3s left on bottom, so that's a 3. And again, that becomes 1 over 27. So as long as you're using the rules, the order in which you use the rules doesn't matter. All right, as long as you apply them correctly. On part B, you have several different values there, and we're all the same basis. They're being multiplied, so we can go ahead and add these together. I'm going to go ahead and do that first. So we have x to the -3 plus -4 plus 2. So -3 and -4 is -7. Add 2, that's now -5. We have a negative, don't want to leave a negative, so flip it, it becomes +5. So 1 over x to the +5. On C, you have a set of parentheses with another exponent on the outside. So again, the exponents get multiplied. So we have 4 to the -2 times -5 becomes 4 to the +10. Right. Now, could we have gotten that other ways? Yes. In fact, I'm going to go ahead and show some work over here off to the side. So 4 to -2 to -5. What if we had decided doing some flipping? All right, we have negatives, so this would become 1/4. I should say 1 over 4 to the +2. We then have a -5 still out there. This would cause us to flip the whole thing. So we'd have 4 to the 2nd over 1. Again, now with a +5. The 5 goes to everything, so we have 4 to the 10th over 1 to the 10th. So 4 to the 10th. 1 to the 10th is just 1. So we don't even have to include that. It's just 4 to the 10th. Same answer as over here. Totally different scenario, totally different direction. Use different rules, but again, same answer. As long as you use the rules correctly, you should get the same answer. On D, we have -4 and 6. So yeah, we're raising to another exponent, so we're multiplying the exponent, so that's -24. If we flip this, it'll make our exponent positive, and we can stop there. For E, now notice there's a lot of different values going on here. So I'm going to go ahead and do subtraction. Again, there's more than one way you could tackle this as well. X, the -4 minus 2, y, 2 minus -5. So we have x to the -6, y to the, this will be +5 actually, because minus a negative becomes plus a positive. So we have x to the -7, sorry, x to the -6, y to the -7. Well, this one can go to the bottom, and it'll end up becoming x to the 6th over y to the 7th. Now again, is that the only way to look at it? No. If you wanted to, we could have moved them first. So the two negatives, if we wanted to, we could have moved those first. So example down here, if we had moved them, we would have had the y value that was still on top as a positive was y to the 2nd. The x value that was on bottom as a positive was x to the 2nd. The x to the 4th was negative. It was on top, so we could move that down to the bottom as a positive. The x that was on bottom as a negative, we could have changed that to a positive by moving it up to the top. And then it would have simply been adding those exponents. So we'd have y to the 7th and x to the 6th. And oh, I made a mistake over here. Look at that. I moved the wrong one. This had the negative. The X had the negative. Glad I showed that other option because I did that one backwards. So the X goes to the bottom. The Y goes to the top because that was still positive. So again, the one that had the negative sign changes places. But again, notice either way, you should come up with the same answer. All right, F. For F, we have the -2. I'm going to go ahead and distribute that first. Again, there's several ways you could have done this. But 2, and then 3 times -2 is -6. And then for the X, -2 and -2 become +4. Notice I'm starting to show a little bit less work. I'm still showing work, but just not as much. So I have a -6. That's going to go to the bottom. So I'm going to rewrite this as 4, or X to the 4th still on top. 2 to the -6 on bottom. If I wanted to simplify that, that's 2 times 2 is 4, times 2 again is 8, times 2 again is 16, times 2 again is 32, times 2 one more time is 64. And this should have said positive there. Once I moved it down, it was a +6. All right, last one, and then the assignment. So we have 3x squared over y to the 2nd power, 4x to the 3rd over y minus 2, all raised to the -1 power. So again, lots of different things we can do. I'm going to go ahead and take care of the exponents on the outside first. So first, let's rewrite this as this 2 is going to go to the bottom one, so y to the 2nd. It's also going to go to the top, so 3 to the 2nd, x to the 2 times 2 is 4. On the other fraction, this is going to flip it, so we have y there's a lot of things going on here, but y to -2, and then this one becomes 4x to the 3rd. Now, I have another flip because of the -2 on this, so I could rewrite that one more time and bring that down to the bottom. If you want to just save some space and just move it down to the bottom, I'm fine with that. So I'm going to cross that off, bring it down to the bottom as a +2. So now all of our exponents are positive. We can go ahead and combine some values though still. You also, if you want to, you can treat this as one big fraction. All right, so I'm going to go ahead and combine them first. Across the top, I have 3 squared x to the 4th. On the bottom, I got 2 y's that are the same, so when I multiply those, I'm adding the exponents. I'll have 4 x to the 3rd, y to the 4th. Now, I have the x's I can go ahead and subtract. I can also go ahead and simplify this 3. 3 squared is 9. For the x's, x, it's just going to be x because 4 minus 3 is just x. On the bottom, I still have the 4, and I still have the y to the 4th. That's our final answer. All right, that was a lot of work on that one. Now, this is the assignment. It's out of the textbooks. It looks like by the time we're at about 40 minutes, so you should have some time in class to work on this as well. Make sure you try to get as much of it done as possible and then get it turned in on Canvas. So these are all out of the book. You should have the books underneath your desks. If you don't have a book underneath your desk, there's still a few in the corner of the room under the flag. So make sure you get one from over there. But again, that is your assignment, so make sure you get that done. I'll also have this posted to Canvas in case you forget.